Okay, just maybe one moment. Okay. Okay, again, welcome to Geometry, Arithmetic, and Differential Equations of Period Seminar. And okay, today Adrian Clingher, he's going to talk about, you didn't put your slides.
Okay.
I think K-tree surfaces of higher Picard rank.
Yes. Thank you for Hossein for inviting me to give this talk. Can you see my slides on the screen now?
Yeah.
Okay. So I'm going to talk about some, actually some special families of K-tree surfaces of high Picard rank. And this is based on some recent work that I have done with Andreas Malmendier, but also some older papers that I have authored jointly with Charles Doran. So let me perhaps start by maybe 2 or 3 slides of just introduction. I'm going to be looking at algebraic K-tree surfaces over the field of complex numbers. So what are those? Those are just smooth, compact, complex surfaces. The canonical class is trivial, and if you're a topologist, you can just say they're simply connected. If you're an algebraic geometer, you can just say that H1 of OX is 0. And usually we consider those with some polarizations, which I'm going to be talking in a moment about. So one crucial part about K-trees, as is well known, is the main cohomological information is in the second cohomology group, which together with the intersection form when doing cohomology over Z gives us a lattice, which is fairly famous. It's called the K-tree lattice. It can be factored as a direct sum of 3 hyperbolic lattices, which are the rank 2 lattices with this intersection form, and 2 copies of the so-called E8 lattice, which has this dinking diagram. The E8 lattice depends how one writes it here. By just writing E8, I mean the negative definite version of it. So overall, the K-tree lattice is unimodular, even it has rank 22 and has signature 319. So if we go a bit further, we have the first-gen class map that goes from the Picard group essentially to the second cohomology. And the image of this map is the so-called Néron-Severi lattice, which is the sublattice of the K-tree lattice. The rank of the Néron-Severi lattice is the Picard rank. And for polarized, for algebraic K-trees, this number goes between 1 and 20. So as you may guess from the title of my talk, I'm going to be focusing on some special families of K-trees for which this Picard rank is close to 20, so fairly high. The signature of the Néron-Severi lattice is 1, and then the Picard group, the Picard rank -1. In terms of Hodge theory, K-tree surfaces are quite nice to work with. We have a Hodge decomposition that splits the second cohomology over complexes into H20, H11, and H02. And the fact that the canonical class is trivial ensures that H20 and H02 are one-dimensional. And essentially, the entire Hodge decomposition is determined by the period line H20. So if we look at this period line, this is essentially an element in the projective space over H2. And it satisfies the standard Hodge linear bilinear relations, which in this situation for K-trees, they can be just written in this way. The Néron-Severi lattice can, of course, be recovered from the periods, and one easy way to get it is to just intersect the second cohomology over integers with the H11 piece of the Hodge decomposition. And that recovers the Néron-Severi lattice. This is the Lefschetz theorem for 1-1 classes. So let me talk a little bit about polarizations. Usually in algebraic geometry, when we say polarization, we usually refer to just one line bundle that we fix on the variety we're looking at. So in the case here, the most common such situations would be to consider what's called a quasi-ample polarization, which would mean essentially a line bundle determined by an effective divisor that is big and nef. And that is sometimes, most of the times, good enough for K3 surfaces because of the following theorem of Meyer, which says if I have such a quasi-ample polarization, then for a certain multiple of the divisor, the linear system will be base point free. And if I consider the map into the corresponding projective space induced by this linear system, then this map is going to be quite nice. It's going to contract certain rational curves, essentially those rational curves that have zero intersection with the divisor D. And this will essentially give us a birational model of X inside the projective space, which might be singular, but all singularities are going to be very tractable. They are going to be rational double points. So quasi-ample polarizations give fairly good models, birational models for K3 surfaces. However, just the standard,
Adrian,
yes.
Quasi-ample, you mean this is the semi-ample, or is this something else?
I'm just gonna say it's big and nef. So big means its self-intersection is positive, and nef means the intersection with any effective divisor is positive or zero. And I believe via the Nankai-Moisezon that means well, the Nankai-Moisezon criterion will say that if you have big and positive self-intersection with effective divisor, then it's ample. So I think this means pseudo-ample, as you mentioned. I think it's equivalent with that. Okay, but now for as we will see in a moment, and actually I believe everybody attending this seminar knows that. So when it comes to K3 surfaces, sometimes fixing just one line for polarization is maybe not satisfactory enough. The reason for that, as we will see in a moment, if I only consider K3 surfaces polarized by just such a quasi-ample line bundle, then the moduli spaces will be quite high. They will be 19-dimensional. So depends how you look at it. It might not be very easy to understand. So in order to get moduli spaces that are more tractable and easier to understand, and moduli spaces where you can, I don't know, do more constructions, sometimes one considers an extension of the standard polarizations called the lattice polarizations. This is a concept due to Beauville and Dolgachev. And what it means is, instead of just fixing one line bundle, we're going to fix an entire sublattice of algebraic classes inside the Néron-Severi lattice. So to have a formal definition, let's suppose that capital M is an even lattice of a given rank, and signature 1, rank -1. And then an M polarization on a K3 surface X is going to be an embedding I of this lattice into the Néron-Severi lattice of the surface. The embedding has to be primitive, and the image of M has to contain a quasi-ample class. So in that sense, a lattice polarization is kind of an extension of the standard polarization. So what is this going to do? Well, as we will see in a moment, this will create nicer moduli spaces. But before I do that, since I'm talking about the K3 surfaces of high Picard rank, and we'll see that for Picard ranks that are 19 and lower. There are some nice moduli spaces that we can consider. But since I'm talking about high Picard ranks, let me just start by saying just a couple of words about what happens in rank 20. If you look at K3 surfaces of rank 20, sometimes these surfaces are called singular, although it's not the best terminology to use. It's a terminology introduced by Shioda and Inose. So what happens in this situation? The rank 20 K3 surfaces, they don't form moduli spaces. They don't appear with family. They don't appear in families. But nevertheless, they can be very nicely classified via work of Shioda and Inose. And that is done by looking at the transcendental lattice of the surface, which is the orthogonal complement of the Néron-Severi in the second cohomology. So if the Picard rank is maximal 20, excuse me, then the transcendental lattice in this situation, it's going to be even, positive, definite, and what is important, it's going to have rank 2. So basically, it's going to be a positive, definite quadratic form. So up to conjugacy, it can be represented by a 2x2 matrix of this type. And now there is an important theorem by Shioda and Inose that says that, well, actually, this transcendental lattice, this quadratic form, even in positive definite quadratic form, actually fully classifies the K3 surface up to isomorphism. So the SL2Z conjugacy class of the transcendental lattice is an invariant for K3 surfaces of Picard rank 20. I just wanted to mention this since I kind of want to cover the high rank situations for K3s. So now, if we abandon this maximal rank 20 and we move to having Picard ranks that are not 19 or lower, we can actually construct moduli spaces. So let me go very briefly over the Torelli arguments for constructing moduli spaces of periods. So if I fix such a polarizing lattice, according to the definition I had before, so if I fix a capital M even lattice, which say rank R, which is 19 or lower, and signature 1 R minus 1, and if I take a primitive lattice embedding into the K3 lattice L, then I can always take the orthogonal complement of the image. Let's say I denote that by T, and this will have to be an even lattice, which is going to have rank 22 minus R, and the signature is going to be 2 20 minus R. So one can define the concept of marked M-polarized K3 in this situation. So if I have a K3 surface X, then a marked M-polarization, it's going to be an embedding of M inside the second cohomology, together with an isomorphism of lattices between the second cohomology and the actual K3 lattice. And the two maps I, the lattice embedding, and phi will have to be compatible in this sense. So a marked M polarization is just an M polarization, as I talked earlier, together with an isomorphism between the second cohomology and the K3 lattice. So for a marked M polarization, then one can actually define a Hodge structure of weight 2 on this lattice T that we have defined, and it's going to have all the properties of the K3 Hodge structures. So T, if I tensor with complexes, it's going to have a Hodge decomposition into 3 pieces, 2, 0, 1, 1, and 0, 2. And we can define a period point corresponding to the K3 lattice by just considering the period line that defines T to 0. And in this way, one gets a period domain for M-polarized K3 surfaces, all I have to do is take the lattice T and look at the projective lines in the complexification of T, and then impose the Hodge-Riemann bilinear relations. And this I'm going to be referring to as the period domain for M-polarized K3 surfaces. So one can see quite easily that this is an open variety of dimension 20 minus r, complex dimension. In terms of symmetric spaces, it also has a description as a symmetric homogeneous space in terms of the group O2 20 minus r. And it actually has two connected components. Each of them is a Hermitian domain, which sometimes is called the Hermitian domain of type 4 20 minus r. So now some Torelli machinery is coming in. First, we have a theorem of Nikulin, Burson, Rappaport, and Todorov that say that, well, one can construct actually fine moduli spaces for marked M-polarized K3 surfaces. Let's say I denote such a fine moduli space by Km. This can be done by gluing sometimes local deformations for these surfaces. But what is important from our point of view here is that if I consider the period map that attaches to a marked M-polarized K3 surface, its period in the M-polarized period domain omega M, then this map is going to be fairly nice. It's going to be étale and surjective. So it's not an isomorphism for marked M-polarized K3 surface. However, if we remove the marking, we'll lose the fineness of the moduli space, but this period map becomes an isomorphism. So if I remove the markings and I consider a coarse moduli space for just M-polarized K3 surfaces without markings, then this is going to be a quotient of the fine moduli space. So let's suppose that I denote this coarse moduli spaces for M-polarized K3 surfaces by M, round M with the index capital M. Then we are going to have a period map that goes from the moduli space into a quotient of the period domain. And Dolgachev tells us what this quotienting group is going to be like, what we have to quotient with. In general, the group we have to quotient with is going to be the set of isometries of the lattice T, integral isometries, which, if we look into the discriminant group of T, they act as identity. So this is the group that we have to divide the moduli space, the period domain by, and once I do this factorization, then the general theorem of Torelli for M-polarized K3 surfaces gives us a very nice picture. So we have a moduli space for M-polarized K3 surfaces in whatever ways we can construct it. And the period map is going to be an isomorphism of quasi-projective varieties that maps into this quotient of the M-polarized period domain by the group I indicated earlier. So this is the general Torelli theory for M-polarized K3 surfaces. I apologize if I just bored you with this. But I wanted to make this introduction to set up what I want to talk about. So in this talk, I'm going to consider special M polarizations. So I'm going to choose some special lattices of high Picard ranks for M. And we're going to try to, well, to classify such families, to see what their properties are, and also to understand their moduli space in terms of period. So in general, if I fix an M polarization, then according to the Torelli theorem I just discussed, this is the moduli spans essentially. And this is going to be a quasi-projective variety over complexes with dimension 20 minus r. So the higher r is, the simpler this quotient it's going to be. And because it's a bounded symmetric domain all the time, that's going to be a nice object to look at. And also because we have this discrete arithmetic group that we're dividing with, this tells us that there will be connections to modular forms of lower order or of higher order. So as the interesting direction of doing research, one would like perhaps to understand these quotients well, maybe in smaller dimensions, but also in slightly larger dimensions. And surprisingly, for various M polarizations, one obtains that this quotient is actually very well known to number theorists, to arithmetic geometers, and modular forms are involved, so you can make connections between modular forms and K3 surfaces. Also, another direction that is interesting to consider is compactifications for these quotients. This is an interesting question in general for bounded symmetric domains. But here, if we take the rank R to be high, then we can get some tractable quotients, maybe 2-dimensional, 3-dimensional, 4-dimensionals. So we can put to work any kind of compactification machinery and see what we get explicitly. So that is kind of what I would like to explore. Now, let me start to consider some special lattices to polarize by, and then we'll see examples. So although I announced in this talk that I'm going to be looking at high polarizations, so high Picard rank polarizations. Let me start with the simplest case of polarization, where the rank of the lattice is actually not that high, is 2. So I'm going to be looking first at the situation where the polarizing lattice is just a hyperbolic lattice 0, 1, 1, 0. So the reason why I want to start with this is the following theorem that says that, well, if I have such a hyperbolic polarization on a K3 surface X, then actually that associates some geometry to the K3 surface, and the geometry associated is what we call a Jacobian elliptic fibration of X, which means I have an elliptic fibration together with a fixed choice of section. And this can actually be seen from the hyperbolic lattice. The hyperbolic lattice 0, 1, 1, 0, it's actually equivalent up to conjugacy to 0, 1, 1, minus 2. And if I have a Jacobian elliptic fibration, then I will have cohomologically, I will have an elliptic fiber F, which of course will have self-intersection 0. Then the fiber will intersect the section at 1. And on a K3 surface, a section will be a rational curve, so its self-intersection will have to be minus 2. So you can see where this rank 2 sublattice it's coming from. And then there are some arguments, essentially due to Piateteschi-Shapiro, that lead to this theorem that you can actually work the other way around. If you start with an embedding of the lattice, of the hyperbolic lattice H into the Néron-Severi of X, and if the image contains pseudo-ample class, a quasi-ample class, then one can actually prove that there is an elliptic fibration with section that will lead to those classes. So bottom line, for the purposes of this talk, what I wanted to say is, well, if I start with this hyperbolic polarization H, and if I look at the moduli space constructed, say, via the Torelli arguments I just described, then I'm going to get a moduli space that is 18-dimensional. It's an 18-dimensional quasi-projective variety, but geometrically, that essentially it's going to be a coarse moduli space for elliptic K3 surfaces with section, or Jacobian elliptic K3s. So it's a first instance where a lattice polarization connects with geometrical features. By the way, if there are any questions, do not hesitate to just interrupt me. That would be fine. There's no problem. All right. So now moving up to other polarizations, I would like to take a couple of minutes to talk about what is called the Nikulin lattice. Nikulin lattice is a special lattice of rank 8. And it's negative definite. Its simplest definition is given here. So let's suppose that we pick 8 free generators that are orthogonal, and each of them has self-intersection -2. Well, then if I take half of the sum of those, this, and I consider this as a 9th generator for my lattice, well, the lattice spanned by these 9 generators is the Nikulin lattice. It's a lattice of rank 8, which has some importance in the theory of K3 surfaces, part of which we will see here. So from my point of view, the reason why I want to consider this lattice is the following. Let's consider the case when I want to choose my polarizing lattice for a K3 surface to be the hyperbolic piece, 0, 1, 1, 0 of rank 2, direct sum with this Nikulin lattice. Well, then one has the following theorem that is due essentially to Nikulin, but appears quite nicely put into a paper by Van Hiemen and Sarti. So every such polarization of this type, hyperbolic plus Nikulin, direct sum plus Nikulin, is equivalent with a Jacobian elliptic vibration on the K3 surface with an order 2 section. So what does that mean? It means I will have an elliptic vibration like before with a section, which I'm going to refer to as a base section. But then there will be a second section appearing. Now, every time when I have a section every time when I have a second section on an elliptic vibration, we can look at the intersection between each fiber and the original base section as defining an elliptic curve structure on each fiber. We have a neutral element in each fiber. So then one can consider translations by this second section in each fiber. And then fiber-wise, one can show that these translations can be put together and they lead to an actual automorphism of the K3 surface. And the group of automorphisms such defined by translating via additional sections in the elliptic vibration, they form what is called the Mordell-Weil group of the elliptic vibration with section. And here, polarization by the lattice capital H plus Nikulin turns out to define an additional section which has order 2 in the Mordell-Weil group. From the point of view of, say, explicit descriptions, the standard model for such an elliptic vibration will be this one. So this is a Weierstrass description of the elliptic vibration. Well, not quite Weierstrass, but a cubic description. And here you can see that you don't have just one standard section at infinity, you also have a second section at 0. So this kind of elliptic vibrations, Jacobian elliptic vibration with a section of order 2, can be understood quite nicely via this model, as we will talk about in a moment. So bottom line, the reason why I wanted to consider this polarization, which is a polarization, lattice polarization of rank 10, is this theorem by Nikulin and Van Hiemen Sarti, which says, well, every time when I have such a polarization, there is an interesting geometric object that appears. There is an elliptic vibration arising on the K3 surface, and this elliptic vibration will have an order 2 section.
Sorry, can I ask you a question?
Yes.
You go in the opposite direction, so you basically claim that once you have an order 2 section, you also have 8 rational fiber components.
Yes.
Can this be seen geometrically?
Yes. So I'm going to be talking in a second about this.
Oh, okay, thanks.
So it's perhaps an interesting fact that is happening here, because the dimension seems to jump quite a lot. If I'm looking at Jacobian elliptic vibration, so no condition whatsoever on the sections, then the moduli space is 18-dimensional. But suddenly, when I add one more section, a section of order 2, the dimension of the moduli space goes to 10. So it's a bit of, I don't know, maybe a counterintuitive thing to look at, depending of how you look at things. But the reason why this happens is, well, there is 2 ways to look at it. One way is to see the generic member in this family. So it turns out that the generic member in this family of Jacobian elliptic vibration with sections of order 2 has 8 special fibers of the Kodaira type I1. That means fibers of this type. And other 8 fibers of Kodaira type I0. That means fiber of this type. And then you can see in this picture the 2 sections. I have one section in green and one in red. So this is the general situation.
In the second picture, they don't look quite like sections. They intersect fiber too much.
Oh, maybe I did something wrong. Yeah, I think I did something wrong here. The sections do not picture this way. So this is where the 2 sections intersect. But yeah, you're right. Yeah, so this picture is not correct. But this is what this is the generic member. You have 8 I1 fibers, and there are 8 I0 fibers. Maybe the way the 8 I0 fibers intersect the sections, it's not like this. So let me thank you for pointing that out. So another way to look at this is the following. If you have a section of order 2 in an elliptic vibration with section, then, as I mentioned earlier, this leads to an automorphism of the K3 surface that is obtained by fiber-wise translating by this section of order 2. And this, since we're talking about translating in a point of order 2 in each elliptic fiber, this is going to be an involution. So this gives rise to what is called a symplectic involution on a K3 surface. A symplectic involution is an involution, let's say alpha, that takes any holomorphic to 0 form, any holomorphic to form to itself. And such symplectic involutions of K3 surfaces are known to have exactly 8 fixed points. This is the theorem of Nikulin. So this gives rise to 8 particular fixed points, and this explains why the dimension in the moduli space will jump. But in terms of the 8 special curves that I guess the question was about, you can see these 8 special curves in the 8 I1 fibers. I hope that's clear. So if I see what the base section is, say in this picture, I can consider that the green section is the base one. Then the 8 special curves that define the Nikulin lattice will be the rational curves that do not meet the base section. And one can prove that, well, the sum of these 8 can be divided by 2, and it's still an integral class in the cohomology, and that defines the Nikulin lattice I was talking about earlier. Does this answer the question? Okay. So
the main issue is that in the singular fibers,
so maybe
it's reducible, so it produces more and more algebraic curves, and so the dimension becomes 10, the dimension of the moduli space.
Yes. Now I don't remember exactly how the sections appear here. I think they probably meet like this, but I'll have to double check this.
But anyway, what is the role of this intersection in all this? I mean, why do you need to have the two sections intersect the singular fibers? What is the reason?
I don't really need them. I just wanted to have this duality between the 8I1 fibers and the 8I0 fibers, because as we'll see in a moment, this H plus N polarized K3 surfaces, they are subject to an interesting duality. So they appear in pairs.
I see.
And moving from one pair to the other, essentially, it's going to be an exchange between these 8I1 fibers and the other 8I0 fibers. So I'm going to talk about that on the next slide. So this theorem of Van Keven and Sarti, I kind of already discussed. Every time when I have an H plus N polarized K3 surface, by translating in this section with this section of order 2, one actually gets to have an involution of the K3 surface, which is symplectic. So now this leads to an interesting phenomenon. So let's suppose that I'm looking at what happens on a smooth fiber in my K3 surface X. So what's going to happen? Let's suppose that the blue curve here is one smooth fiber in the elliptic vibration, and I have the base section in red and the section of order 2 in green. Well, among the points of order 2 in this smooth fiber, there will be 2 more points, which I indicated in purple. So what happens when I consider the involution? Well, the involution will be translations with the S1 section. So if I take the quotient, I'm going to get a new elliptic vibration, right? An isogynous. I'm going to get an isogynous elliptic fiber. Let's call it maybe E prime T. So the two sections, the base section S0 and the section of order 2 S1, they are going to give on the other side just one section, just 1 point on the new quotient fiber. But then the 2 points, the two remaining points of order 2 will be matched under the quotient, and they will give another special point in this quotient fiber. So this quotienting now can be done fiber-wise. So what this does, it creates a new elliptic vibration on a new surface Y. And this new elliptic vibration is going to have, again, 2 sections. One that can be considered as the base section, what I denoted here by S prime 0. And then there is another section which turns out to be, again, a section of order 2, S1 prime. More than that, every time when you quotient a K3 surface by this kind of symplectic involution, as I mentioned earlier, it is known that such an involution will always have exactly 8 fixed points. Well, if one takes the quotient by the involution, we will get a singular surface that has 8 singularities, but the singularities are simple, are A1 rational double point singularities. So if I resolve those singularities, a simple computation actually shows that we will get another K3 surface. So via this, what could say is a fiber-wise 2 isogeny business. We have 2 sections in the original K3 surface, and we quotient each elliptic fiber by the point of order 2 that exists, we get a new elliptic fibration on a new surface that turns out to be, again, a K3 surface. So this leads to a duality, which has been described by Van Heeven and Sarti and is based on the Nikulin observation by Nikulin. So I'm going to refer to this duality here as the Van Heeven-Sarti-Nikulin duality, or VSN in short. So what this does is, every time I have a K3 surface with a Jacobian elliptic fibration with an additional section of order 2, you can play this game and construct a new K3 surface Y that has the same features. It has a Jacobian elliptic fibration on it and a section of order 2. And the relation between these two K3 surfaces is going to be given by two rational double cover maps. So essentially, we have fiber-wise two isogenies going in one direction and in another. So what this duality says, the one I was just trying to explain, is saying that if we look at the K3 surface that have this rank 10 lattice polarization, if I look at polarization of this type, capital H plus the Nikulin lattice, then there is a natural involution on the moduli space here. But the moduli space is still 10-dimensional. So what I wanted to talk about is consider the case where the lattice polarization I'm going to consider is an overlattice of H plus M. So a lattice capital M that contains H plus Nikulin, but perhaps is much higher in rank. And then the question I would like to explore is, well, I want to understand the moduli spaces of this M-polarized K3 surfaces, which I discussed from the beginning, but then also see what the duals under the Van Heeven-Sarti-Nikulin duality will be like. And as we will see in a moment, we get quite an interesting situation. The M-polarized K3 surfaces turns out for high Picard rank can be described nicely in terms of quartics in P3. So they appear as K3 surfaces of degree 4. They are fairly easy to describe and classify. They have strong connections with modular forms. Their duals, however, usually appear as degree 2 K3 surfaces, double sextics. And they are not that easy to classify, perhaps, but they have quite a richer geometry. For instance, they have much more rational curves. The group of automorphisms is much higher, so on and so forth. So now let me go to some actual examples to see how high polarizations lead to nice moduli spaces and strong connections to modular form. And I'm going to start with perhaps the simplest examples, the situation when I consider a lattice polarization of rank 19. So the K3 lattice was hyperbolic plus hyperbolic plus hyperbolic plus 2E8. Why don't we look at a lattice polarization that has this form? So hyperbolic plus 2E8, and then to get to rank 19, we add another one-dimensional piece which has a generator of self-intersection minus 2M. So if one goes through the Storelli machinery I described perhaps 15 minutes ago, the moduli space of periods turns out to be a quotient that is quite known in number theory or arithmetic geometry, is the quotient of the usual complex upper half plane by the so-called Fricke modular group, which is obtained in this way. You first look at the PSL to Z matrices, for which C is divisible by n, so that will be the usual congruent subgroup, order n. And then you consider the Fricke modular group, which is generated by this order congruences and congruences, plus this additional involution matrix, which has coefficients in R. So the free K modular group is a subgroup of PSL to R, and this gives the actual quotient, the actual one-dimensional quotient that describes these surfaces. I'm not gonna go into very much details for this class of K3s because this will appear very nicely in the context of a rank 18 example. But let me just say here that, well, for people that are familiar with this quotient, say from number theory, one could see that, well, this also classifies pairs of n-isogenous elliptic curves. And this quotient, which I guess in number theory is known as x0n plus, actually makes a coarse moduli space for pairs of n-isogenous elliptic curves. And this is actually not surprising, because if I look at this family of K3 surfaces and I want to analyze them from the point of the duality I just considered, turns out that the VSN part, or the Van Gievensart inequaling partners, are Kummer surfaces corresponding to a product of two elliptic curves, the two elliptic curves being n-isogenous. All right, so this is an example of rank 19 lattice polarization, where the moduli space is an interesting one-dimensional modular curve. Let me go to a second example of polarization of rank 18 now. So I'm going to be looking at the lattice capital M hyperbolic plus E8 plus E8. So it turns out that if I look at this K3 surfaces, excuse me, you can actually classify all of them very explicitly. You can write a family of quartics that constructs all of them. And this family is given here. This is some work I've done some years ago with Charles Doran. So we start by just selecting a triple of complex numbers, A, B, D, where D is not 0. And then one can actually construct a quartic surface, which has 3 varying coefficients, A, B, and D. And, well, if one looks at this these quartic surfaces, turns out that they are not so bad to understand. The singularities in these quartic surfaces are rational double points. In fact, we'll see in a moment that it's exactly 2 of them generically. And when resolving those singularities, what one obtains is a K3 surface, or a family of K3 surfaces, carrying a canonical H plus E8 plus E8 polarization. Maybe the polarization is not explicit here. How can you see this configuration of curves appearing from this quartics? Well, one way to see that is to look for singular points in the quartic equation I've just given. And turns out that generically there are just 2 singular points, which I denoted P1 and P2 here. One is at 0, 1, 0, 0. The other is as 0, 0, 1, 0. And there are also 2 lines in P3 that are indicated in this picture. The first line that contains P1 and P2, and the second line that passes through P1. And if one performs this desingularization, the following configuration of rational curves appears. So here I have the desingularization of the first singular point. Here I have the desingularization of the second singular point, and in blue I have the 2 lines. And now if you look at this diagram, this is a dual diagram that tracks rational curves on this K3 surface. And you could see the hyperbolic plus E8 polarization. Perhaps the 2 E8s are easier to note on the left and on the right. This is the first E8, and this is, I believe, the second E8. I should have gone a bit more. And then in order to find the hyperbolic piece, the elliptic fiber and section, I'm indicating that here. So the section S is a curve in the diagram, and then the elliptic fiber, all we have to do is take one of the extended E8 pieces and consider the divisors with the weights given in this diagram, and one can see that these two classes generate a hyperbolic lattice. So bottom line is we have this family of quartics that depend on three parameters, A, B, and D. The quartics indicated here. And all of them, upon desingularization, lead to K3 surfaces of Picard rank 18 or higher, and the polarization is H plus E8 plus E8. So now it turns out that these quartics have some nice properties, almost modular kind of properties. So first of all, one can prove that up to isomorphism, this three-parameter family covers all situations. All K3 surfaces polarized by H plus E8 plus E8 appear in this way. And if I take two members of this quartic family, say X of ABD and X of A tilde B tilde D tilde, these two will be isomorphic as lattice polarized K3 surfaces. Turns out if and only if the two triples ABD and A tilde B tilde D tilde are linked in a weighted projective way. So A tilde differs from A by multiplication by a non-zero quantity T square. B tilde is T cubed B, and D tilde is T60. So this leads to an invariant. I can consider the three coefficients and take the weighted projective point in the weighted projective space 2, 3, 6 with the condition D being non-zero. And turns out that this two-dimensional space is a coarse moduli space for K3 surfaces polarized by H plus E8 plus E8. If I want to look at periods, the situation here is quite simple from the point of view of periods because the polarization is rank 18. So the moduli space of periods is going to be two-dimensional. If one works through the general Torelli procedure I discussed at the beginning of this talk, one can actually find a nice description of the moduli space of periods in this situation, and it turns out to running again into a known object in arithmetic geometry or number theory. We get what is called a Hilbert modulo surface, the standard Hilbert modulo surface, which is we take two copies of the usual upper half space, and then we quotient that by the Hilbert modular group, which is PSL to Z times PSL to Z, semi-direct product with a group of order 2 generated by the interchanging of the two upper half space pieces. So if I have two elliptic curve periods, tau 1 and tau 2, one in the first upper half space, the other in the second upper half space, then the element of order 2 here switches the order of the two tau 1. So this is a modular surface, it's two-dimensional surface, and the Torelli theorem for in the case of this lattice polarization tells us that this modular quotient is isomorphic with the coarse moduli space that I indicated on top of this slide. So now the connection that appears with the SL to Z modulo forms, the standard modulo forms, is the following. Well, if my coarse moduli space in this situation is given by this weighted projective triples, ABD, and then the moduli space of periods is given by the Hilbert modulo surface, which is a quotient of periods which are pairs of two tau 1 and tau 2. What would be a description for the period map? Well, the period map will have to go from the triples ABD to tau 1 and tau 2. We know it's an isomorphism, so why don't we describe the inverse of the period map? Well, it turns out that the inverse of the period map, which tells how to compute the weighted projected triple ABD from the two periods tau 1 and tau 2, is pretty much given in terms of the generators for modular forms on SL2Z. So this is the formula. A essentially is G2 for tau 1 times G2 of tau 2, where G2 is the modular function 60 times the Eisenstein series E4. Then B is given by 27 G3 of tau 1 times G3 of tau 2. Where G3 is again the classical function 140 times the Eisenstein series E6. And finally, D is the product of the two discriminants. Again, the classical delta functions, delta of tau 1 times delta of tau 2. So we have a coarse moduli space for this H plus N polarized K3 surfaces, and the moduli space can be quite nicely interpreted in terms of periods. You get a classical object in number theory, this Hilbert modular surface, and then the inverse period map is describable in terms of the modular forms associated to this object, or associated to this group, which essentially is PSL2Z here. Well, if we look at this space of periods over here, we have already seen that there must be a connection with two elliptic curves, because we're talking about a period domain, which essentially is coming in pairs, tau 1 and tau 2. Tau 1 and tau 2 in the usual upper half space. So that already suggests that there must be a connection between these K3 surfaces and pairs of elliptic curves. Well, it turns out that one way to see this connection is via the Van Heever-Sartini Cooling duality. If I look at this polarized rank 18 polarized K3 surfaces and I apply the Van Heever-Sartini Cooling duality that I was talking about 10 minutes ago, turns out that the dual partners are Kummer surfaces associated to just the product of two elliptic curves. So that's another family of rank 18 K3 surfaces. And in fact, if I wanna read the three coefficients ABD in terms of the J invariance of these two elliptic curves, if I want to see what these two elliptic curves are explicitly from the quartic coefficients, one can read the two J invariants via these formulas. So since I'm allowing to interchange the two elliptic curves E1 and E2, the two symmetric functions sum and product will be describable in terms of A, B, and D. All right. So now I want to decrease the polarization. We have seen an example of rank 17 polarization, rank 18 polarization. Let's see an example of rank 17. Maybe Hossein, can I ask when I'm supposed to finish?
Well, your 1 hour is already.
Oh, okay. All right. So let me just go over very quickly over this example, and then I'll say just a couple of more things and I'll stop. Is that all right?
Yeah, okay. We just
okay. So well, turns out that this particular situation that we noticed here, that if you take a polarization of high Picard rank, you can describe the K3 surfaces in the family, and you might get a space of periods that is quite nice and describable in terms of number theory and modular form. This was not just a coincidence for the example we just saw. So if I relax the lattice polarization a little bit, if I take, for instance, this lattice polarization, hyperbolics plus C8 plus C7, so this is a rank 17 case, then the entire discussion I just did can be extended. So again, you can classify these K3 surfaces in terms of quartics, and now there's going to be 4 coefficients in this quartics, which I'm denoted A, B, C, D. Again, these 4 coefficients have a modular interpretation, so they change according to a weighted projective space situation, but now the weights are 2, 3, 5, 6. One can get a modalized space, which is a 3-dimensional moduli space in this situation. And if I look at periods, well, if I look at periods, the domain of periods should be 3-dimensional, and turns out the moduli space of periods in this situation is the Siegel modulo threefold. Again, a classical object in number theory. And well, these 4 coefficients A, B, C, D turns out, well, they are related with the so-called Igusa modulo forms for symplectic 4. So they can be described explicitly in terms of the generators of the even modular 4 for symplectic 4. So I guess what I want to say, just to summarize what's going on, again, you can get a space of period that is 3-dimensional in this situation, is connected with principally polarized abelian surfaces in this situation, and it can be described, the period map can be described in terms of Siegel modular forms in this situation. And there is a connection via the duality between via the von Neumann-Sartini Cooling duality between these K3 surfaces of rank 17 and principally polarized abelian surfaces. Well, the dual for each of these K3s is the Kummer of a principally polarized abelian surface. And the situation can continue further. I guess I'm out of time, so I had at least 2 more examples prepared. You can go to a rank 16 situation and kind of do the same discussion. Again, you can describe these surfaces, and the moduli space is going to be 4-dimensional now, and the 4-dimensional period domain, again, it's going to have a strong number theoretic interpretation. You get a period, a moduli space that is 4-dimensional and has been explored by Matsumoto, Sasaki, and Yoshida. And again, the inverse period map can be described in terms of modular form associated to this object. And one can go further. I had at least 1 more example, which I worked recently with Andreas Malmedier, when the rank is 14. And again, you get in this situation a 6-dimensional moduli space, which is more interestingly to explore because we are in an area where nothing is really known about modular forms here. But bottom line, I guess I will stop here. I hope.
Okay, thank you, Adrian.
Yeah,
so let's
thank
start.
you.
So,
if anybody is interested in seeing the other examples, I can, Hossein, I could email you the slides if anybody is interested. Yeah.
Okay, any question before I ask a question? Maybe Adrian, the space of automorphic form in this rank 16, and the other one, this is rank the other one is
14.
described by Musa's work.
Yeah.
You know, the algebra, it is generated by which automorphic forms?
Yes, yes. So in the rank 16, the even automorphic forms, the dimension is 5. I'm sorry, 6. Well, let me show you. No, I'm sorry, it's 5. They are here. So this is the rank 16. So in the rank 16, if I'm looking at the automorphic forms for this group that appears, this Matsumoto, Sasaki, Yoshida group, the generator, there's 5 generators that build this modulo group of, I'm sorry, the ring of the graded ring of even modulo forms in this object. And this is actually not surprising. This kind of modulo forms have been discussed in a series of papers by Winberg. So this was an example that it was kind of known, the modular form part of the discussion. But if you go further, then as far as I know, not much is known about these modular forms, and things become quite complicated. But we have 2 more examples where we know what's going on.
Okay. Walter, you wanted to ask a question?
Yeah. Is there any well-known or at least suggested relation with this and mirror symmetry, for example, that you have mirror symmetry?
There is a relation between this and what is called Dolgachev mirror symmetry for K3 surfaces, which I'm not sure whether is a version of the actual mirror symmetry for Calabi-Yau threefolds, but there is a paper by Dolgachev. It's called Mirror Symmetry for Lattice Polarized K3 Surfaces. That is a mirror symmetry actually between families of K3s. You cannot go point to point. You go family to family. And the duality I was talking about here, what I call the von Neumann-Sartre-Nikulin duality, is a particular case of this Dolgachev mirror symmetry for K3s.
Thank you.
Sure.
Okay, maybe let me first stop recording and go to the informal question session.
Okay.
That the people feel better to ask questions.